Lesson 2.2 talks about modeling with power functions. So I'm trying to, with 2.1 we talked about linear functions and then quadratic functions. Okay, so this one we get to define what a power function is, and then also down at the bottom we're going to define what a monomial function is, and that will lead us into 2.3 then. But so definition of a power function. Power function is of the form f of x equals k times x to the a. And note specifically it says there where k and a are non-zero constants. So that means k and a are numbers. Those numbers can be anything except 0. They can be positive, they can be negative, they can be whole numbers, they can be fractions, they can be decimals. Anything except 0 is your definition there. Okay? A is considered the power, and k is the constant of variation or the constant of proportion. I've seen it called both. When we talk about this, I'm going to throw in some direct and inverse variation review from algebras, but f of x varies as the 8th power of x. So f of x varies as the power of a, or the a power of x. I don't know, it's hard to say 8 and not make you think the number 8. You know, so it's the power of a of x. Or another vocabulary, f of x is proportional to the a power of x. Okay. Independent variable is x. That just means x is independent variable. That's what you plug into the equation. Y is dependent upon x. Power functions with positive powers are direct variation. If you remember back from Algebra 1, we probably talked about a little bit in Algebra 2, but the form of the equation y equals kx, okay, this is f of x equals kx, but that is direct variation, where it's often said as y varies directly with x. That k is your constant of variation or constant of proportion. When there's a positive power there, it's direct variation, because that's going to end up being k times x. When x has a negative power, then it's inverse variation. And it's inverse variation because it's going to end up being k divided by x, because x, the negative power, we move it to the denominator, right? So you can also think of this as y equals k divided by x. Okay? So a little bit about that. We're going to really do some equation writing, like they're going to give us a scenario. We're going to write the equation, or in this case the power function, and then we're going to do a little bit of identification of powers and constant variations. So looking at example 1. From empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum varies directly as the square root of the pendulum's length L, provided that the swing is small relative to the length of the pendulum. Express this relationship as a power function. All they're asking us to do is to write an equation. Take these words, lots of words, that's the problem, right? Take all of these words and put them into an equation. Okay. Go back, look for some keys here. From empirical evidence and the laws of physics, it has been found that the period of time t, what are they telling us to use there? T, right? So the period of time t for the full swing of a pendulum varies directly. That's a phrase we've used before, yes. Okay, that's going to tell us a little bit about the setup. So varies directly as the square root of the pendulum's length L. Did they just throw another variable at us? They did. What's it say about that variable? Square root of the pendulum's length L, provided that the swing is small relative to the length of the pendulum. Express this relationship as a power function. Okay. So, So we look at what I've underlined. The period of time t varies directly as the square root of the pendulum's length L. Okay. Well, use this up here as a representative. Right here, this f of x equals kx for direct variation. This would be written as y varies directly with x. Okay, so when we talk about y varies directly with x, that's where your equal sign, and then there's some constant of variation there, or constant of proportion. So for ours, what do we have? We have t, specifically capital T, because that's what they told us, yes? If they give you a specific capital or a lowercase letter, use that appropriately. Okay. For the full swing of a pendulum, varies directly. So varies directly, that's kind of your hint of we're going to say equals. And then there's going to be some constant of proportion or constant of variation. So I'm going to use, of course, K. That's your typical one. And what's it vary directly with?
Square root of L.
The square root of L. So that's going to end up being T equals K times the square root of L. Now, I'm going to tweak that a little bit. I don't want to leave it in that form, because if we go back and look at it asks us to write this as a power function. We go back and look at this as a power function. It needs to be of the form f of x equals k times x to the a. Well, we almost have that. The only thing I'm not happy with is square root of L. What do you know about the square root of L? You're on the right track.
L to the power of 1/2.
Does that ring any bells, guys? The square root of L is equal to L to the 1/2. Because where does this index of 2 come, or this denominator of 2? It's the index on the square root, right? So if it's a square root, it's a denominator of 2. Officially, the 1 is just the power on the variable. So it's L to the 1/2. That rings a bell, yes? So we can write this as T equals KL to the 1/2. And that is your power function there. Okay? Okay, let's look at the next part. Example 2 asks us to state the power and the constant of variation for the following power functions. So it's specifically calling these power functions. We're being asked to state the power and constant of variation. Okay, so do keep in mind, we're talking about power and constant variation on these power functions. According to your notes up above, these are supposed to be in the form of f of x equals k times x to the a, correct? Okay. Thoughts?
The power would be 1.
Not fully.
1/3.
Can we really think about this as a power function quite yet? Is this of the form of k times x to the a? Not yet. I would rewrite this and think of this as f of x equals x to the 1/3. There is a power of 1 on the x, but we need it as x to some power without that radical in there. So that is going to make my power to be 1/3, and that is my A value. So I'm going to say that A is 1/3. What about my constant of variation? What would you say that is? No? Huh? No? No?
3.
Not 3. What else was said?
1.
1? Why is the constant of variation 1?
There's a imaginary x.
Yeah. There's that invisible 1 that is just that. It's invisible, isn't it? Okay? Your constant variation is that number, that coefficient in front of x. In this case, our coefficient is the invisible 1. It's there. It's just we don't write the 1. So it's that invisible 1. Got it? Okay. Let's try B. Thoughts on B? G of x equals 2 over x squared.
Power is negative.
What?
Power being negative 2.
Power is negative 2. And what I was waiting for, my recommendation, can you rewrite this in a different form? Okay, we need to write it in that form to match k times x to the a. The 2's already up there. How do we get x to the second out of the denominator? That's making that exponent negative, yes? When you take a denominator across that fraction bar, it changes sign. So it changes from positive 2 to negative 2. So with that in mind, that means my power is now negative 2. So my a is negative 2. What's my constant of variation?
2.
It's that 2, right? So k is 2. KC, h of x equals negative x to the negative 4/10. Thoughts on my power?
Negative 2.
Okay. Is this actually already in a good form? Kind of weird. The other ones weren't, but A, we already have a power, negative 4/10. It's okay if my power is negative, isn't it? It's okay if it's a decimal, so it's good. What's my constant of variation? Constant of variation is negative 1. We have a negative out front. You, of course, know that needs to be a negative 1. And D, m of x equals negative 3. What?
Would A equal 1?
If a equals 1, then that means that there's an invisible x to the first. Is there allowed to be an invisible x to the first? No. If it's an invisible x, what is that power? X to the 0. So what does that make a? 0. What's the catch?
Oh, it's not in power.
Okay. By definition of a power function is f of x equals k times x to the a, where k and a are
Number.
non-zero. Non-zero constants. What did we just come up with?
It's not a power.
We came up with the power being 0. Is the power allowed to be 0?
No.
No. So this falls into the grasp of this is not a power function. Okay, so watch out for that. If a works out to be 0 or k works out to be 0, it's not a power function, which if k is 0, a is going to be 0 as well. So, okay, so basically everything's going to be a power function unless it's just a constant, right? This is the one thing that's not going to be a power function. Okay. Questions there? Okay. One other topic here, and that is definition of a monomial function. So power function, very specific that that power has to exist. It cannot be 0. With a monomial function, monomials are the smaller pieces of polynomials. So we often talk about polynomials like y equals x squared plus 2x plus 5. We talk about polynomials where there are multiple terms added and subtracted together. And we'll talk about those more in the next lesson. Today it's a monomial function, and a monomial function is just one term. And it's one term and can be either of the form f of x equals k, or this covers everything. F of x equals k times x to the n. Very similar to last time, isn't it? It's still of that same form like k times x to the a. They just used n here. But look at your requirements. K is a constant. So k being a constant means it is just a number. So that number out front can be positive, negative, fraction, decimal. Could k be 0? Doesn't say it can't. So 0 is a constant. So that can be any number. And n, so what was a last time? N has to be a positive integer. What do we mean positive integer? What are integers? We know what positive means. More specific than just numbers.
Numbers above 0.
Whole numbers? If it's an integer, right? Integers are positive or negative whole numbers. Whereas positive integers are just going to be whole numbers. Now, I have included here 0 listed as well. Okay, so when we talk about positive integer, basically whole numbers. So things like 0, 1, 2, 3, so on and so forth. Okay, so a little bit different setup you have to watch out for, because now that power has to be positive and a whole number. That power cannot be negative, that power cannot be a fraction, that power cannot be a decimal. Okay, I only got one example here. State the degree, coefficient, and independent variable of the monomial function y equals negative 3x to the 5th. Ironically enough, my Algebra 2 is reviewing some of this vocabulary today too. Okay, what do you remember about degree?
Is it 5?
It's 5. It's that power, yes. So the degree is 5, or in other words, it is basically your n value, right? Okay, it's your power, it's your n value. Coefficient. What's my coefficient?
Negative 3.
-3. The coefficient, I try and use that word a lot. It's that number out front of the variable, yes? Number, it goes right in front of the variable. In this case, it would be your k value, wouldn't it? So k is -3. And independent variable. What's my independent variable going to be?
X.
It's your x. So we had a degree of 5, a coefficient of -3, and our independent variable is x. Okay, that's a little bit of everything in this lesson. As I said, there's not a lot to this lesson. We're just doing some bare basics in lesson 2.2. Your homework is page 177, 1 through 22. Crazy things happen. You have some work done. So grab a book, grab an iPad, grab something, right?